This problem asks us to find the maximum upward force before one of these three ropes fails under a tensile load of 450 newtons or more. So we need to find what is the maximum value that F can have. I'll call that F max. And we're given the information that the tension in any rope, in any one rope, can be 450 newtons before failure. So we have here, looking at our situation, a particle equilibrium type of question. We have three ropes all connected at A, and we have an upward force that's also directed through A. So all of the forces in this are going to be concurrent. They're all going to pass through A. So we can model A as our object of interest, or our particle of interest. So we need to start with a free body diagram of what's happening to point A. And I'm going to use the given coordinate system here and just stick with that for all of my coordinates that are going to be important in this problem. So I have my origin down here, nothing's happening there. I have my point A, my particle of interest. I'll need its coordinates. I have D over here. I have C. Oops, C is somewhere over here. And I have B. All right, so I'm going to have a rope going from A to point C, another rope, and therefore a force going from A to B, and then a force going from A to D. All right, so the forces that act on A, I'm going to have this upward force F caused by, let's say, the hot air in the balloon. I'll have a tensile force from the rope that goes from A to C. I'll call that TAC. I'll have a force going from A to B. And these forces are going to look a little bit on top of each other. So a TAB here, tensile, and a force going from A to D, which I'll call TAD. All right, so those are going to be the forces acting at A. I have to label this one. That's F. And I will redraw this TAB. Okay, now we're in 3 dimensions, so it's going to be really helpful to put the coordinates of these points here. It's going to make finding the position vectors and then the unit vectors much easier. All right, so point A, based on the given coordinate system, is purely in the positive z direction. So it's going to be 0, 0, 6 meters. And moving on to point B, based on the coordinate system, I have to go a negative 1.5 in the x direction. I have to go a negative 2 in the y, and it's in the xy plane, so 0 in the z. To get to point C, I have to go positive 2 in the x. I have to go negative 3 in the y, and again it's on the xy plane, so 0. And point D is going to be on the y-axis itself, so 0 in the x. I have to go here a positive 2.5 in the y, and then 0 in the z to get to point D. All right, so I have my complete free body diagram now. I have my coordinate system. Oh, I do need to label positive axes here. All right, now I have my coordinate system. I have my point of interest, A. I have the forces that act on A, the 3 tensions and the applied force, the upward force. I've labeled my forces off the bat. I don't know the 3 tensions and I don't know that upward force, but if I don't know it, I'll just label it with the variable name and I'll be able to find it later. And I have all the coordinates, which I'm going to need to find my directions and then unit vectors. All right, so now with a complete free body diagram, we can move on to our equations. So here I recommend, because we're in 3 dimensions, it's going to be easiest if we just find all the component forms of our vectors, of our force vectors that we're going to be needing to use before we even write our equilibrium equations. So for this, I am going to want to find the unit vector AB, AC, and AD. F is purely in the z direction, so I don't need to go through extra work to find that. So we can find U hat AB. Okay, so it's pointing the same direction as our force from A to B, so it's going to be the coordinates of B minus those of A. So B is going to be a negative 1.5 minus 0, so negative 1.5i, minus 2j, minus 6k. And then we're going to have to divide by its magnitude. And I'll jump right into Mathematica for this, since I'm going to have to find a bunch of these unit vectors. So RAB negative 1.5, I minus 2 minus 6 in the K. And I can find its magnitude here is 6.5. And I'll just here, UAB is going to be normalize RAB. So I don't get nice fractions in this case. I am going to get these decimals here, but this is U hat AB. I'll just, again, let Mathematica do the work on this one, but we need to just know how do we set this up. So that's where these decimals are going to be coming from, so I'll just rewrite them here. So it's going to be a negative 0.231. In the I direction, and a minus 0.308 in the J, and it's going to be minus 0.923 in the K. And we can just double check. Yep, so that's correct. Okay, I'm just going to refer to my diagram here to get the rest of these, rather than trying to do them all by hand. So I can get the rest of these position vectors at this point. So RAC, I'll just put it right into here. So that's going to be C minus A is going to be actually 2 minus 0 is 2. Negative 3 minus 0 is negative 3. 0 minus 6 is negative 6. And then RAD I can put in here. So D minus A is going to be 0 minus 0 is 0. 2.5 minus 0 is positive 2.5, and 0 minus 6, negative 6. All right, and from there, I'm going to be able to quickly find my unit vectors as well using the same pattern. So UAC, I can just normalize RAC. And for UAD, normalize RAD. So now I can just transcribe them now that that's done. So U hat AC came out to, I'll leave it in this fraction form. So 2/7 I minus 3/7 J minus 6/7 K. And U hat AD came out in a decimal form, 0I plus 0.385 J minus 0.923 K. So I found the 3 unit vectors I'm going to need, and this is going to make it much easier and much faster in the next step where I now write my equilibrium equations, because I already know at this point how much of each force is in the I, the J, and the K direction. So moving on to my actual equilibrium equations now. So I can start in the X direction. And I'm in static equilibrium, so I know it's going to equal 0. So now all the X components of my forces I can add together. So from AB, I have 0.231 TAB, that's the I component, plus 2/7 TAC, and then AD is 0 in the I, so this is everything I need for my X equation. So just the TAB and the TAC appears in the X direction. So nothing I can do yet. I have 2 variables, but only 1 equation written, so I can move on to summing forces in the Y direction. So I have for AB, negative 0.308 TAB in the J, negative 3/7 TAC in the J for the TAC, and then plus 0.385 TAD. And that's it. So I have two equations now, but all three unknowns. So I can move on to my last equilibrium equation, Z. So I'm going to have here, so I don't forget about it, I have F. All of F is in the positive Z direction, so I'll include that. I have negative 0.923 TAB, minus 6/7 TAC, and minus 0.923 TAD, again, plus the F. All right, so actually in this case, if we see we have four variables because we have the three tensions and that upward force F that we don't know, but we only have three equilibrium equations, and that's all we can get out of a 3D particle equilibrium problem are those three forces X, forces Y, forces Z. So I'm out of equilibrium equations I can write, but now I can use the information that was given to us about the rope breaking, because this is, in one sense, a design problem. I want to know what's the maximum force, that upward force that can be applied before the first rope breaks. So this is another one of those situations where we cannot and should not assume that all three ropes are going to break at once. They're not going to have the same force in them, likely. It's possible, but unlikely. So one of them is going to have to break first, either AB, AC, or AD. And we don't necessarily know at the onset which one is going to happen first. So I am going to have a couple of different possibilities here. Well, one of the three has to break first. If I don't know up front, then I'm going to come up with these different situations. So situation A, I'll say that TAB is the one that breaks first. And then I'm going to apply that and then test it. So I'm going to add a fourth equation. If TAB breaks first, or is just on the verge of breaking really, I'm going to set it equal to its maximum value, that 450 newtons. And then I'll test each of these situations for AB breaking first, AC breaking first, AD breaking first, and I'll be able to test them and see which one actually would happen first, because I can assume one breaks first, but then see what happens to the tension in the other ropes. Yeah, so I can make these force equations. I can actually do this in vector form if I want, or I could do it in scalar form. But what I can actually do is take TAB times its unit vector plus TAC times its unit vector, and I'll make these lowercase, plus TAD times its unit vector, and just see what happens here. All right, so if we see what Mathematica did, each one of these cells here is actually, it's not quite done yet, but this looks like equation 1 for the most part. I have the AB and the AC here. I have here the AB, the AC, and the AD that I have in equation 2. And I have equation 3 here. I'm actually missing the F, so let me put that in. So 0, I, 0, J, F in the K direction. So now we see the third equation here is actually that equation 3. It has the AB correctly, the AC correctly, and the AD. It is carrying some more decimals, and that's okay for now. I'll just leave it as it is. All right, so here I have 3 equations for four of our unknowns, and I can call this EQ1. And actually, I know that each of these is equal to 0. So this is actually a vector equation here because I have 0i, 0j, 0k equals my right-hand side. And then I have each of these equations happening. Now I can put in my equation 4a, where I'm setting TAB equal to 450 newtons. So this is not going to necessarily be too easy to solve, or too hard actually, because equation 4a, if I know TAB, I can take that into equation 1 and find TAC. Once I know TAB, TAC, I can go to equation 2 and find TAD. Once I know those 3, I can go to equation 3 and find F. So doing this one by hand would not be too bad. I just really prefer not to. So I'm going to say solve the equation 1, which is actually the 3 equations and EQ4A. Okay, so Mathematica did this all for me, and I want to tell it to only give me back 3 decimal places of precision here. That'll just make things easier. Okay, so what I told it to do with this solve here is take the 3 equations contained in equation 1 and that 4th equation in equation 4a and solve these 4 equations at the same time for the 4 variables, TAB, TAC, TAD, and F. And it solved those 4 equations at the same time and gave me these results. So let's just see what we have here. So TAB is 450. Well, that's better be the case because that was this condition. We were assuming TAB failed first. However, if we look at the results here, TAD comes out to 765. So let's write that down as what happens when we solved for situation A. I'll just write down that result, 765 newtons. Well, that doesn't work because for AB to be the one that breaks first, TAD would have already failed. TAD is already above its maximum allowable of 450 by being equal to 765. So condition A cannot be what happens. TAB cannot be the one that fails first, but we still need to test it. All right, so let's move on to the other possibilities. In B, let's assume that TAC is the one that breaks first. Now, probably we can tell here, even from our solution from A, since TAD was the highest one, that TAD would be the one that should probably be breaking first. But I'll test all 3 of the possibilities and just make sure that we prove that's the case. But likely, TAD, the C condition, is actually the one that's going to be realistic. All right, so I'll just put an X here because that's not what happens. All right, so if TAC is the one that breaks first, I have a new 4th equation because 4a is not valid in this scenario, because in this scenario I say that AC is the one that's just going to be on the verge of failing first. All right, so I have to make a new equation here. I need an equation for B, and this is where I set TAC to the 450 newtons. So I can take this solution I just came up with here, and I can now solve for a different set of 4 equations. So the first 3 equations are still valid. Equilibrium equations are always true if we're in static equilibrium. So I'm still keeping the EQ1, that has not changed, but I'm now setting a 4th equation with it, equation 4b, where I'm going to say, well, what happens if TAC is just on the verge of failing? And I'll solve these 4 equations 1, 2, 3, 4b at the same time. All right, so if I do that, we see AB and AC is just at its limit, but AB and AD are above their limit. So AD is 947. So I'll just write it down here. TAD is 947. So again, it's already past its limit. So we already could have seen that coming from the first solution, but I just want to be thorough here. So what must be true, because there's only 3 possibilities, is that TAD would be the first one to break. Right? Which means that for C, I am going to set TAD to the limit of 450 newtons. And now I can solve for another equation paired with those first 3 equilibrium equations. So TAD is 450 is my 3rd scenario. All right, so taking, again, those first 3 equilibrium equations and now having a 4th equation, equation for C, I can take this in, and just by seeing what the results are, I have the upward force. TAB is below its limit, TAC is below its limit, TAD is directly at its limit. So I'll just copy these in so that we can see them all written down nicely here. All right, so TAD is 450. I want to write these down just so I know what the different forces are for the one that worked. 214 newtons, and a B came out to 265 newtons. All right, so all three of those are below that limit of 450. So we know that that wasn't true in A. TAD had already failed by the time AB just was on the verge of failing. Scenario B, AD had already failed and AB had already failed when AC was just on the verge of failing. But here, AD is on the verge of failure in scenario C, and the other two are below their limit. And this is going to happen when that upward force is 843 newtons. All right, so that is the maximum upward force that we can apply before the first rope, which turns out to be AD, is going to break. And again, just going back quickly to the results here, in scenario A, the rope AB broke at about 1430 newtons, and in scenario B, it took 1770 newtons. So this is really the lowest force that caused breakage was 843 newtons, which means it's the maximum force that we can apply before one of our ropes will break. All right, so we started out just like any other 3D particle equilibrium problem. We needed to find the unit vectors first so that we can see what the components are going to be of all of our forces when we go to the next step, which is summing forces in the x, the y, and the z direction. Again, using the components from the unit vector multiplied by these unknown magnitudes, in this case TAB, TAC, TAD. Our z equation had, in this case, an upward force F that we also had to include. So from our three equilibrium equations, in this case, we had four unknowns. Oftentimes we'll have only three, but this is that design type of problem where we actually have four. So we had to get a fourth equation. We already used up our three equilibrium equations. There's no more we can do from our free body diagram. So now we had to use the rest of the information of the problem that we were trying to find what the force was that would cause our first rope to break. Well, there's three ropes, so we tested each possibility once. What if AB was just about to break? AC, AD. So it turned out that scenario A couldn't be feasible because a rope already would break by the time AB was at its limit. Scenario B didn't work out because two ropes would break by the time AC was at its limit. So C, which we did test, had to be the scenario that happened, that AD would be the first rope to break. And we saw that that would happen with an upward force of 843 newtons on the balloon.